Good morning. Hello, Professor. My name is Varun, and my teammates Ninad and Sumit. They picked the dataset, the New York City taxi dataset, and the problem we are tackling is the tipping problem. And let's go to the data collection. Uh, the TLC dataset is a treasure trove offering details from such as timestamps, geographic coordinates, etc. Uh, and the summary. The This dataset is a cornerstone for analysis, providing researchers and practitioners with a wealth of information about the city. And the hypothesis, our research is centered on the hypothesis that tipping is a multidimensional outcome influenced by factors such as trip duration, temporal considerations, and socioeconomic context at pickup and drop-off sites. This hypothesis serves as a beacon guiding our analytical process to identify the minute details contributing to the observed variety in tipping patterns in the dataset. Let me talk about the summary of what we gathered from the dataset. The average trip distance is 3.55 miles with a high standard deviation of 4.70. The average fare amount is $20.1 and with a high standard deviation of 19.29, which indicates a good amount of fare variability. The average tip is $3.52 with a standard deviation of 4.18, which has a few negative and high positive tip amounts. And the general observations from what we got is there's a good significant amount of variability in the trip related metrics, which suggests a good range of taxi trips. Next, I'll be handing it over to Ninad.
So, hello, I will be discussing the problems which we found with the dataset and how we tackled them. So, our dataset exhibited a large amount of skewed target variable, that is the tip amount, with many outliers. So, we prudently retained some of the outliers to prevent the overfitting while removing those that significantly skewed the analysis. Talking about the feature importance, analyzing feature correlations and distributions helped us identify low impact features, and we removed this to enhance the model's predictive accuracy. These features included tax amounts and other unrelated charges and other features that we removed in the data pre-processing. Talking about the overfitting, monitoring the training and the validation stats losses enable us to detect the overfitting, and a simple hyperparametric tuning techniques were employed to mitigate the issue. Talking about the GPU usage, due to the large amount of dataset size, the GPU usage was crucial. We utilized the T4 GPU on the Google Colab servers. However, a more powerful computational resources would be required to gain a deeper statistical analysis. Coming to the model building process, we have the data exploration. So descriptive statistics, data insights, and correlation heat maps were produced using the Python. And this provided us an initial overview to start our process. The data pre-processing includes utilizing pandas and other libraries to load the data set into the time and extract the time-related features, encoding categorical variables and everything else. And the outliers were removed using the IQR method for both features and the target variable. Coming to neural network model, so removing outliers during the pre-processing model obviously improve the model robustness, but developing a sequential neural network using KRAS with appropriate sequential layers and dense layers. We use the MSE loss function as a loss function and the Adam optimizer, and also added the GPU acceleration to facilitate the model training. So coming to the model training and evaluation, the model was trained over 50 epochs using the training set, and evaluation of the batch size was around 8,000, which was pretty normal because the data set was all textual data set, and such a large amount of batch size could be handled by the GPU. Doing the visualization, we assess we can see the mean squared error on the test set using the KDE plots and the KDE plots. So we can see that the model does a pretty good amount of predicting when the fare amount goes really high, but during the low amount of fare, there is a high variability of the tipping features, and hence the tipping behavior cannot be accurately predicted for the low ranges of the fare amount. doing the model comparison, we can see the heat maps of the features with true and predicted tip data or trip amount, and we can see that the fair amount and the trip distances really are correlated with the predicted amount, and this proves that the tipping does indeed depend upon the fair amount and the trip distance. So we did many further visualizations, including the scatter plots of the true tip amount versus trip distances and the trip distances and the fair amount. But we can see that the inclusion of the high outliers really did mess up the training of the model. But it's still during a low in the low region in the common region, like the lower region of the data set, that is low fair amount and low trip distances, we can see a really good prediction amount. And hence I will now pass it over to Sumit to continue sharing about this.
Thank you, Nina. So I'm going to discuss about why we chose neural network model over other potential models. So there were two models we could have chosen. They were linear regression and support vector machines. So so I'm going to first we'll discuss about linear regression. So linear regression assumes a direct linear relationship between features and outcomes. It works well when patterns are straightforward and dependencies between factors depend solely on a single feature. But since in our case, in our data set, the relationships are likely more intricate due to dynamic nature of taxi rides in bustling model metropolis. So the average tipping amount depends not only on single feature, but it depends on multiple features like trip distance, rate code ID, location, etc. Now coming to support vector machines offer interpretability and computational efficiency, particularly for data sets of moderate size. They are robust against overfitting and can capture nonlinear relationships effectively with the right kernel. But since the data set was very large, the computational demands of SVMs become a limiting factor as they might struggle to handle this large data sets efficiently. Uh, so, so we chose neural network model over these two models because they are adept at learning intricate patterns and can navigate the multifaceted nature of this data set. Now coming to conclusions. So, this dataset offers comprehensive details of taxi journeys. However, it presented its own set of challenges from data imbalances to outliers. We addressed these hurdles meticulously through robust processing techniques, ensuring the reliability of our analysis. Um, Despite grappling these computational limitations, this model was selected for its handling capacity and the intricate relationship within our datasets. Its ability to navigate the complexity of various tip variables made it the ideal tool for predicting tip amounts. Uh, Now, when it came to evaluating our model, we use metrics like mean squared error and employed visualizations like KD plots and scatter plots. These tools allowed us to not only validate our predictions, but also unearth insights into tipping patterns and the significance of various features in influencing tipping behavior. So now coming to our findings provided invaluable insights into the nuanced interplay of factors that affect tipping behavior. These insights are crucial not just for drivers looking to optimize the earnings, but also for broader discussions on urban transportation economics. While our exploration had its limitations, it serves as a foundational stepping stone for future research endeavors. So there were a few things which we couldn't do in this project due to reasons we mentioned. So that left the scope for future work. So in future projects, we can do a couple of things, which are first is seasonal variations. So we can extend our data set to cover a full year's worth of taxi trip data across all 12 months. So that we can uncover how tipping patterns fluctuate during peak periods like summer tourisms or winter holiday seasons. Secondly, geospatial integration, incorporating geographical coordinates of pickup and drop-off locations as additional features in our predictive models can significantly boost accuracy. Next, model refinement and optimization. Exploring more advanced machine learning algorithms or ensemble techniques like gradient boosting or random forests could potentially improve prediction accuracy. and also fine-tuning hyperparameters and conducting extensive model validations are key step forwards towards building more robust predictive models. Lastly, last point, interactive visualizations and interpretability. Developing interactive visualizations or dashboards can simplify the interpretation of model predictions and feature importance. This accessibility allows stakeholders, including taxi drivers and policymakers, to grasp tipping behavior trends intuitively. It empowers them to make informed decisions based on these insights. So with this, we conclude this video. Thank you for watching.
Thank you so much.
Thank you.